Welcome back to another fun and exciting Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I am your temporary host, Heidi, joining you today with Professor Fred Watson, astronomer at large, while our usual host, Andrew Dunkley, is off on his world cruise having a grand old time. Fred, how are you doing today?
I'm very well, thank you. I'm still inundated with people interested in the end of the universe, which we talked about a few episodes ago. So that's good to know that people are taking some notice of the fact that 20 billion years might be the closing down ceremony for the universe. We'll cover that in Space Nuts, obviously.
We'll talk about the end of the universe. Well, today we've got more great questions. I always say that our questions are what makes up half the show. And our very first question of our episode today comes from Casey from my side of the world, from Colorado, which is a beautiful state. And I always tell people, if you see beautiful pictures of the mountains, they're definitely from Colorado, not from Utah. Utah's full, don't go. So
Okay.
Casey from Colorado says, "Hi guys, I know that white holes are basically the opposite of black in the way that nothing can enter them. I understand that at this point they are completely theoretical and we haven't actually found any. If we did find one, what would be inside of it? Would it have mass? How does gravity work in and around it? Love the show and hope you're both well. Thanks."
That's great. Thanks very much, Casey. And it's a good question. It's probably about 30 years ago that white holes were all the rage. People were talking about them endlessly. And I guess what that did was set up people looking for them. And we've never found any evidence of one. But the reason why people think that they might exist is that there's nothing in the equations of relativity, which is what govern the behavior of black holes and space, and generally it's Einstein's theory of gravity. There's nothing in that says that you can't have a sort of opposite object to a black hole. But what you have to do in the equations is reverse the direction that time works in. And if you switch that round, and yes, that's hard to get your head around at all, but if you do that, put negative time in, instead of a black hole, you get a white hole. And so the theoretical physicists said there's nothing that we can find that would rule out the existence of these objects, that they may exist. And then there was the connection that perhaps two black holes or two white holes or a black hole and a white hole could connect with each other to make a wormhole, which might give us a way of getting from one side of the universe to the other very quickly. I think you'd risk all kinds of horrible things happening if you did that. But anyway, that's the idea. So the quest was on for looking for evidence of white holes, which you would think, unlike a black hole, would be very bright. And so far we found nothing, no evidence of anything that would correlate with the observations that physicists suggest might be made of a white hole. If we did find one, as Casey asks, what would be inside it? Well, yeah, it's hard to know because black holes, it's a one-way process for stuff going in. With a white hole, as you say, Casey, it's a one-way process with stuff coming out. So where's that stuff come from? What's inside it? Where has the material that might be escaping from it, if it was, where did that come from? Maybe from a wormhole, maybe just from sucking it in from the fabric of space. I'm not qualified enough in relativistic theory to be able to give you an answer to that. Would it have mass? Yes, I think it would. I think the mass is one of the constants in the equations of the white hole. So I think the answer is it would have mass, and so gravity would probably work around it in the same way as a black hole does. I'm sort of speculating here, Casey. These are not authoritative answers because I have not had a look at the white hole theory for a long time. But I think you can draw all kinds of comparisons. There's an analog, from a black hole to a white hole. The fact that we've never found anything that has symptomatic or is symptomatic of the existence of a white hole probably means that in reality they don't exist. But we're always open to suggestions.
We could just be in the wrong universe for them.
That's true. In a different universe, maybe white holes are everywhere. Yes, quite so.
And they can't find any black holes. There's some podcast where there's a Fred's interviewing Heidi, and they're wondering, well, why can't we find these theoretical black holes?
Yeah, that's right. And time's running backwards for us.
Yeah, we're getting younger.
That'd be good.
Our next question, you must have listened to a few episodes ago where we were talking about name history. This is from Martin. Martin says, "Hi, Adelheid and Frederick. I just listened to your latest episode, Stellar Questions, and the very first one puzzled me. This is about time dilation. The formula Fred used for calculations takes into account only velocity. Isn't it only for observation dilation? The reason it puzzles me is that the scenario was traveler returns back to Earth. Isn't that more like twin paradox? And the differences should be explained by acceleration. Because without acceleration, and given the velocity is relative, we couldn't tell if it was the astronaut who traveled or the Earth who went for a trip and returned to a stationary protagonist. I hope I'm not completely off. Great work with the podcast. I love it."
And Martin, great work on the question, because everything you've said is absolutely correct. I just didn't say all that because it didn't seem as though there was time to do it. But yeah, you're right. You've got to have, for the twins paradox to work, and that's where one twin goes off on a long journey into space very quickly at 99.9995% of the speed of light, if you want to have a 100-year ratio or 100-to-1 ratio. The astronaut goes off, visits a distant star, takes their photographs and with their smartphone and all the rest of it, comes back to Earth. The Earth has aged by 100 years and the astronaut has only aged by a year. That's called the twins paradox because you imagine that it would be two twins who were being separated like that. And it only works because of the accelerative component. So the answer I gave was purely special relativity. That's simply relativity with motion at a constant speed. So clearly you're not going at a constant speed. If you turn around and come back again, you've got a deceleration and then an acceleration. And those are the terms that allow the twins paradox to work. It's the fact that you're actually switching acceleration, because that introduces geometrical elements which are more related to general relativity. And in fact, what I also didn't mention, so just to fill you in, Martin, that there is more to the story, exactly as you've said. In general relativity, that's Einstein's second theory of relativity, the one that accounts for gravity and that lets black holes exist and white holes and all the rest of it. That theory also has time dilation in it. In other words, what it says is that if you get in a strong gravitational field, your clocks run more slowly as observed from outside than they would if you were just outside the gravitational field. So, for example, our clocks are running slightly more slowly than the clocks on board spacecraft orbiting the Earth. And that has been measured. That time dilation has been measured. And I think it is taken into account in the GPS in your phones as well. I think you have to have those relativistic corrections in there for it to work. So yes, good pickup. Thank you very much, Martin. And thanks also for giving my Sunday best name as well. Very few people call me Frederick. It's usually people in banks or in medical reception areas because that's my full name. Is your full name Adelheid, Heidi?
My full name is Heidi, but the
Yeah,
name comes from Adelheid,
yeah,
which I believe means noble, is the kind of the history of the name.
yeah,
Um, but I know it's a German name. I know my mother read the book Heidi when she was young,
yeah,
and
yeah.
she loved the character, so that's how I got the name Heidi. Despite I'm actually my family heritage is Italian.
Oh, there you go.
I'm second generation Sicilian, so I still have family in
Ah, okay.
Sicily, but I have a
Ooh,
German first name, an Italian last name, and an Irish husband. So I'm a classic American, you can say.
yeah, that's good.
Now let's take a break from the show to tell you about our sponsor, NordVPN. Now, I think we'll all agree that exploring the universe is thrilling, but exploring the internet without protection, that's a black hole you don't want to fall into. Sorry. As a Space Nuts listener, we have an exclusive deal for you so you can stay protected, and that is NordVPN. It's the fastest, most secure way to browse the web. With NordVPN, you get next-level encryption, blazingly fast servers around the world, and zero tracking, so you can stream, shop, or scroll safely. It's the tool I personally trust when we're diving into the internet, and we want to give you peace of mind. I've used it overseas several times. I've used it at home. It works, and it is seamless. Head to nordvpn.com/spacenuts for an exclusive deal just for Space Nuts listeners. Big savings plus 4 months extra, absolutely free. Don't surf the cosmos unshielded. Secure your digital universe today with nordvpn.com/spacenuts, and don't forget their 30-day money-back guarantee. Go to nordvpn.com/spacenuts. Now back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Our next question is from Ash from Brisbane.
Yep.
And Ash says, "Hi, Heidi and Fred. I hope this message finds you well. I recently came across a statement by Professor Brian Greene regarding the observable universe being 93 billion light years across. He mentioned that if we were to condense the known mass of the observable universe into theoretical black hole, the calculations suggest that the event horizon would align with the distance of the cosmic microwave background. This leads me to wonder, is Roger Penrose correct in his theories? Could the CMB, the cosmic microwave background, actually represent the inside of an event horizon, and that's why we cannot penetrate it? Is this just one big universe-sized coincidence? I'm looking forward to hearing your thoughts on this intriguing topic."
That's great. Thanks for that, Ash. We did talk about the idea of the universe being a black hole or inside a black hole, I think in the last Q&A episode. But I was talking last night to some of my colleagues at the conference that I'm at the moment, the Astronomical Society of Australia's annual science meeting, about this. I think the general opinion was basically what you've said, Ash, at the end of your question there. Is this just one big universe-sized coincidence? I think everybody thinks that it's drawing a long bow to assume that we might be inside a black hole only by the fact that the universe, effectively what we call the proper distance to the event, the cosmic microwave background radiation would be about the size of the event horizon if the mass of the observable universe was in a black hole. So that's one strand to this. But you've highlighted another one as well, Ash, with Roger Penrose. His ideas are very much concerned with big bangs coming from black holes detonating in a universe that just keeps on going. So we've got this multi-universe idea again, the multiverse, with supermassive black holes or hypermassive black holes popping off everywhere, and each one forms its own universe inside it, and we're inside one of those. It's a nice theory. Again, very speculative. There's no evidence to... In fact, it's hard to imagine what the evidence might be to prove that. We have people working on the idea of multiverses, and indeed the Penrose theories as well. But it's very hard to think what evidence you might bring to bear on that says yes or no about living in a black hole. It's a nice coincidence, though, this, the radius of the universe being approximately the radius of the event horizon of a black hole. I think that's all it is, though.
We may never know.
We may never know. That's right.
0G, and I feel fine.
Space nuts.
Well, what I do know is that our last question of the day is from one of our regular listeners. I can still talk. I haven't gotten fatigued. I usually get a couple audio questions mixed in. So these written questions, I'm doing more talking. But I can still say that our last question is from Rennie Traub from Sunny Hills, West California. Sunny West Hills, California. Maybe I'm losing my ability to talk, but it's good because this is a short question. And Rennie says, it seems that there is a purpose for why the universe is the way it is. What are your thoughts on why dark matter functions the way it does and the need for it to not react with the light, but yet it reacts to our matter in the universe?
Yeah, I mean, this is a really deep question, which is sort of concealed in some, very innocent language. I think it's a beautiful question, Rennie, as yours always are. So that first sentence, it seems there is a purpose for why the universe is the way it is. I think the way I would look at that is the other way round. That it's something called the strong anthropic principle that says that we can observe the universe because we are here. It's a like almost like a non sequitur, something that just doesn't follow. But what it's saying is that we are here because the universe has certain physical properties, and it's the laws of physics that let stars form, galaxies form, planets form, humans form, all the rest of it. That is to say that it looks as though we live in a universe that is fine-tuned for life. That if the physical constants were different, particularly if the speed of light was different or the charge on the electron was different or whatever, the universe might never have been able to form planets. It might have either been so short that it collapsed on itself almost immediately, or it may have been so rarefied that atoms never came together to react and form molecules and make up the ingredients for life. So it's this fine-tuning. As I said, it's the anthropic principle. And so in a way, you can interpret that as the universe having, let me just read your sentence again, the purpose for why the universe is the way it is. Its purpose is perhaps a strong word, but it's saying the universe is the way it is. It allows us to be in it. If there was a different universe that we're in, we wouldn't be here, so we wouldn't be able to observe it. So I think that's a fascinating question. It's one that's been written about a lot, the anthropic principle. What are my thoughts on why dark matter functions the way it does and the need for it not to react with light, but yet it reacts to our matter in the universe? Look, that's just a huge mystery, that we have these observations that suggest that there is something in the universe that has gravitational attraction. It attracts things. It's got enough gravity that it stops galaxies from flying apart because their rotation's too high. And yet it does not interact in any way with in any of the other properties. So it doesn't have any reaction, as you say, with light, electromagnetic radiation. So, for example, it doesn't block out the light coming behind it. It would be very handy if it did. Then we could actually see it and measure its properties. What we have to do is look at the way it does interact with light, which is through gravity. means it can act as a lens. If you've got a large blob of dark matter, it can act as a gravitational lens, which means it will focus light and let us see magnified images of very distant galaxies if you've got a large blob of dark matter around a cluster of galaxies in the foreground, because we do know that dark matter is where normal matter is. Wherever there's normal matter, there is dark matter, except in a very few cases. So it's still a mystery, and it is still possible that we've got it wrong, that there is something else going on that negates the need to have dark matter as a property of the universe. And one of those things is something studied by a friend and colleague of mine, Peter Verweyen. He's still, I think, writing his PhD thesis on a theory called MOND, modified Newtonian dynamics, which suggests that at very low accelerations, which are the kind that are experienced by stars going in orbit around the center of a galaxy, for example, at very low accelerations, our normal understanding of Newtonian physics breaks down. So MOND is modified Newtonian dynamics. And it was introduced back in the 1980s when dark energy was first postulated by a scientist whose name was Mordechai Milgrom. He introduced the idea, and it's been floating around ever since. Why isn't it accepted generally as the main reason why the galaxy behaves like it does and why the universe as a whole behaves like it does? That's because if you tinker around with Newtonian dynamics, a lot of other things don't make sense. The early universe doesn't make sense. Globular clusters don't make sense. And so that's why it's not popular. But it's still possible that we might be missing something. Maybe there is something out there that makes us think we're surrounded by dark matter and we're not. So scientists have to be open-minded about that. Not so open-minded that your brains fall out, as somebody once said, but open-minded enough that you can recognize any possibility. And I think that's really what my thoughts would be in the questions that you've asked, Rennie. And thanks again for very profound and thought-provoking questions.
You guys did a great job with your questions this week, and Fred did a great job as always answering them. And I am just so grateful to be a part of this journey. Fred, do you have any, maybe we can give another minute. Do you have anything that you really have enjoyed from this conference that's been like some of your highlights?
Yeah. So the session that I was really keen to be at was yesterday, and it's about the things that I lose sleep over. How is Australia going to be involved with the next generation of large telescopes, large visible light telescopes? These are things that might seem a bit pedestrian when you compare it with the other stuff that's going on at the conference. There's a lot of really interesting new science coming out, and one of them that I sort of seem to pick up a lot on is the idea of how galaxies work, how the outflows of gas from their black holes at the center, this is particularly in the early universe, how that can interact with the gases that are forming stars. There's a process called quenching, which is where these winds that are blown out by black holes actually blow out the star formation process. So you get the star formation process quenched, and that's something that still has a lot of research going on with it. And that was certainly one of the hot topics yesterday. But my fascination is always with because basically I'm a telescope man. It's what I did all my life. I ran telescopes for a lot of my life. And I'm always interested in where our country is going in regard to the facilities that it needs so our astronomers can make these discoveries of the kind that we've been talking about today. So that was, I think, the highlight of the conference for me. Some of the news is good, some of it's not so good. All facilities for astronomy rely on funding, and it tends to be governments that do that funding because many of the arrangements are bound by international treaties, which have to be signed by governments and not private individuals. So we will see where this all goes. And certainly on Space Nuts, we will keep everybody well aware of what's happening in the world of telescopes and the world of astronomy generally.
Thank you so much, Fred. It's been a pleasure chatting with you today. And thank you again to all of our listeners.
Yeah,
and with that, we are going to wrap it up and say goodnight until the next time.
Good night and good morning.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.